Alright, so we're diving deep into the parallel postulate. This is one of the most debated ideas in geometry, right? Euclid's fifth postulate, what makes it so significant to the entire structure of Euclidean geometry.
Absolutely. The parallel postulate is unique among Euclid's five postulates. The other four feel kind of intuitive, but this fifth one about parallel lines just isn't as self-evident. Euclid states it is if a line segments intersect two straight lines and makes the interior angles on the same side less than two right angles, thus two lines, if extended indefinitely, meet on the side where the angles are less than two right angles. It feels more complex.
Right, and I read somewhere that for centuries mathematicians tried to prove it using the only other four postulates. Why do you think that was such a big deal?
I think they wanted to streamline Euclidean geometry, almost as if to make it simpler. If the parallel postulate could be proved using the other postulate, geometry could rely entirely on a more intuitive concept. Plus, there was this belief that the fifth postulate seemed less than universal than the others.
And by less universal, I guess you mean that it feels dependent on specific spatial assumption rather than general, fundamental principles. It seems like many mathematicians weren't satisfied until they either prove it or develop alternatives.
Exactly. Procrus, for instance, thought that the postulate was something that should be derivable from the other axioms, so he and the others searched for ways around it, which is why the postulate role in Euclidean geometry is crucial. It shapes our understanding of congruence, similarity, and of course, parallelism itself.
It's fascinating how much hinges of the single postulate. I mean, without it, Euclidean geometry just isn't the same.
Agree. Now let's think about whether Euclidean geometry can function without it. This is where the necessity of parallel postulate gets questioned. I read about Zachary and his attempts to prove it. He started by assuming it was false so that instead of having one parallel line through a point not or given line, there were either no parallels or more than one.
That's right. Zachary even came up with his own type of quadrilateral, the Zachary quadrilateral, but his logic led him to strange conclusion, which is eventually dismissed as absurd since he was working under Euclidean assumption. It was like he almost stumbled onto hyperbolic geometry without realizing it.
Yes, that's great point. Zachary thought he was proving the absurdity of alternative geometry, but his work inadvertently contributed to non-Euclidean geometry is almost or unique.
And yet, for Euclidean geometry, the parallel postulate still hold as essential component. But what if we go a step further and ask, is a parallel postulate even necessary for geometry? What do you think?
That's really challenging question. I'd say it depends on the type of geometry we're talking about. For Euclidean geometry, yes, it is necessary, but as we see with the non-Euclidean geometries like hyperbolic, elliptic, geometric, can exist without it.
True. It is fascinating how non-Euclidean geometry emerged from his question. In hyperbolic geometry, for example, there are infinitely many parallel lines that can pass through a given point, while in elliptic geometry, there are no parallel lines at all.
Right, and each geometry remains internally consistent, its own world, so to speak. In fact, some of the alternative geometry built on the negation of a parallel postulates have real-world application, like in physics, where they are used to describe the structures of space and time.
That's mind blowing. The universe itself was not purely Euclidean. I think that's why the question of whether the parallel postulate is necessary has such philosophical implication. It challenges our assumption about space and even reality.
Definitely. And it's bring up another interesting idea. Statements that are equivalent to the parallel postulate. Claire wrote another work on restating the parallel postulate in different ways. Have you looked into some of these?
Yes, Clayroots' version was like an simplification, right? He said that through a given point, only one line can be drawn that never meets a given line. It's pretty straightforward and has the same implication as the same original parallel postulate.
It does, and Cray wrote praising made the postulate easier to digest conceptually, but there are also Sakari's quadrilateral approach, where they assume that the quadrilateral with two right angles could be used to verify the parallel postulates.
Yeah, Zachary Quadrilateral becomes a powerful tool. He assumed that if you start with a quadrilateral with two right angles and try to make a consistent geometry, you end up with either Euclidean or hyperbolic conclusions, depending on how the angles add up. It's like creating a test structures for perennialism.
Right, and each of these approaches, when assumed to be true, implies a parallel postulate in the same way. And fascinating because it's like discovering logical shortcuts that all leads back to this one central idea.
Which makes me wonder if these equivalent statements imply the parallel postulate. Could we theoretically swap them out in Euclidean geometry and still get the same results?
In theory, yes, the geometry would still work, but it would be feel different. It's like switching recipes to get the same end product. Each recipe involves different steps of flavors but reaches the same outcome. This flexibility hints at why there are multiple ways to interpret and apply the postulate.
Well said. I guess that also explained why mathematicians were constantly trying to replace or simplify the postulate. The equivalences allow for versatility in application and teaching approaches too.
Definitely. Speaking of teaching, I wonder how we could convey the parallel postulates impact to students who might find it abstract. Would it help to discuss real life analogies or historical contexts?
That's great idea. We could, for instance, talk about how Zachary or Clayrot struggled to prove something that seemed self-evident but was actually exclusive. This historical perspective might make it relatable and show how the parallel postulates connects to the human desire for logical certainty.
Or we could use spatial analogies like in architectures or city planning, where parallel lines play a vital role. Imagine what would happen if two straight designs to be parallel suddenly intersected could make the concept more tangible.
Yes, and by illustrating non-Euclidean geometries like hyperbolic and elliptic as alternative worlds, we could show that the different assumptions lead to different but valid outcomes. Maybe that would make the parallel postulate unique more understandable. Exactly, because it emphasizes that while the postulate feels necessary for Euclidean geometry, it's not universal. It's like a rule specific to this particular type of geometry, which broadens students' perspective. That's what I love about this topic. The parallel postulate is just one assumption that leads to a whole universe of geometrical rules and truths. Understanding its implication, alternatives, and equivalence is like gaining insights into the very natures of mathematical thinking.
Well put, and ultimately, discussing the parallel postulate's history and its application can help students appreciate the value of questioning assumption. It teaches us that challenging a seemingly basic rule can open doors to entirely new fields.
That a core lesson, isn't it? The pursuit of understanding the parallel postulate's necessity and rule his reshaped geometry is like testament to the power of questioning even the most fundamental ideas.
Absolutely. Through the parallel postulate, we see that geometry is not just about shapes and line. It's about concept, logic, and exploration possibilities. It's exciting to think that something as simple as a line and a point not meeting can be profound.